Hey y'all, I'm Gracie and this is Lab 4, Circuits and Capacitors. Introduction. For our main physics principles, we have more generally the conservation of charge, current, and energy, and more specifically, the loop rule, which is the sum of each component's potential difference is zero in a round-trip circuit. The node rule, which is the sum of the currents going in, is equal to the sum of the currents going out, and Ohm's law, which simply states R resistance is equal to the absolute value of potential difference divided by current. The goals of this lab are to predict circuit behavior for circuits in series and parallel, and to use a multimeter simulation to measure conventional current and potential differences, and finally observe behaviors of ohmic resistors and capacitors in an RC circuit. The results. Current I1 and current I2 for the series circuit were equal to 0.02 amperes. The current for the parallel circuit was equal to 0.06 amperes. Capacitors with a 10 ohm and 20 ohm light bulb take half as much time to charge as it does to discharge, and a discharging capacitor's voltage is time dependent. Firstly, our series circuit. Here we have an image of a simple series circuit with two ammeters, each having a current I1 and current I2, two resistors, and two batteries, which each are 1.5 volts for a total EMF of 3 volts. Using the loop rule, we have all of their potential differences equal to zero, which can be broken down into this equation. Because we have a circuit in series, the resistance can be calculated using this equation for a total of 147 ohms. And using that equivalent resistance, we have current 1 is equal to current 2, which are both 0.02 amperes. This is the predicted value, which is confirmed in the simulation. As you can see here, each of the ammeters both read 0.02 amperes. Next, for our series circuit, we removed one of the amps and replaced it with a voltmeter. The voltmeter reads 3 volts because we have a series that is no longer complete, and all the current will surround this break, and that is why the ammeter reads 0 amps. Next, in our series circuit, and we break up the circuit into these sections, and for each of those sections, we calculate the potential difference, and using Ohm's law, we found the currents for each of these sections. This experiment was done to show that the potential difference for all these sections in total is equal to 0 volts because the round-trip potential difference for a circuit is 0 volts, which is a confirmation of the loop rule. Next, in our series circuit, we have a graph of potential versus the position around the circuit. Over here, we have where the battery is, and over here, we have where the voltage decreases due to the resistors, and finally goes back to 0. Finally, in our series circuit, we have a calculation of resistance using Ohm's law and the data used from when we broke up the circuit into little sections. The calculated resistances using Ohm's law is the same as the values given to us in the lab itself. Next, we have a parallel circuit. We place an ammeter parallel to the 100 ohm resistor, and we notice that the current actually increased. This is because there is less resistance in this path due to the node rule. Next, we have our first part of the RC circuit. Over here, we have an image showing how a 2.2 farad capacitor is charged using a 9-volt battery. And in this image, we have a fully charged capacitor that will then be discharged. As we know, when the capacitor is charging, the light glows and then gets dimmer until it eventually goes out. When you discharge, the light lights up again and eventually goes out with time. We used a 10 ohm light bulb and a 20 ohm light bulb, and the 10 ohm light bulb took 5 seconds to charge and 10 seconds to discharge, and the 20 ohm light bulb took 9 seconds to charge and 18 seconds to discharge. These values make sense because the 10 ohm light bulb has less resistance than a 20 ohm light bulb. The final part of our RC circuit experiment was to show the time dependence of voltage for a discharging capacitor. In this image, we have a 30 ohm light bulb and a 0.2 farad capacitor, which was charged with a 9-volt battery. After about 20 seconds, the capacitor discharges, This value makes sense because as time goes on, the voltage in a discharging capacitor decreases. Before we get into the results of the time-dependent relationship of voltage for a discharging capacitor, we have to talk about how we can even make that relationship. Based off an equation that describes how charge decreases on a capacitor as time goes on, we know that voltage also decreases as time goes on. The delta V naught for the capacitor is equal to 9 volts. The potential difference at time equals 1.29 seconds is equal to 7.259. From the differential equation that we talked about earlier, we know that the natural log of the delta V divided by delta V naught is equal to this value. Natural log of delta V divided by delta V naught itself is equal to negative T divided by RC. RC is actually the time constant, which is the time that the voltage difference has dropped to 1 over E of its original value, which is predicted to be around 6. Next, we have the results from our time-dependent experiment for voltage in a discharging capacitor. This chart over here shows the times from 0 to around 20 seconds, the potential differences as time went on, and the natural log of delta V divided by delta V naught, which is graphed over here against time. From the equation on the previous slide, we know that the slope of this graph is equal to negative 1 over the time constant. From our graph, we have the slope is equal to negative 0.1668, and the time constant is equal to 5.995, which confirms our predicted results as they are both around 6. In conclusion, the loop rule and the node rule can be used to examine series, parallel, and RC circuits. The simulation used helped confirm the loop rule and the node rule. As an aside, if this lab was done using a real ammeter, the current would be lower than expected because real ammeters have resistance. In the ideal model, the ammeters as well as the wires both had 0 resistance. Also, if this lab was done in real life using a battery to charge a capacitor without a resistor, the capacitor would charge in less than a second before blowing, which is what the ideal model confirms, as in the simulation, the capacitor charged and blew in about 0.3 seconds. Thanks for watching!